So hello everyone, my name is Gabe Fierro. I'm a fourth-year PhD student at UC Berkeley in the computer science department. I work with David Culler. A lot of his prior work was in sensor networks. How do we sort of create these little energy-efficient things that we can put into buildings, to try to give us a better idea of who's there, how comfortable they are, what's the airflow like. And my talk's going to be about the software-defined building, sort of a look forward. Given the fact that data is going to eat the world, software is eating the world, how do we take advantage of the principles of software development that have allowed the internet to grow, that have allowed these large companies to grow? What are the lessons we can learn and apply to the built environment, the buildings, to help them behave better? The way I'm going to do that is I'm going to be walking through some of the technologies that we've been developing and try to point out some of the larger principles there. So if you have any questions, please let me know during the talk. So here's sort of a view of, one interpretation of how we can look up the range of buildings from sort of the hardware through the control systems, the services that we want to have in our building, and the applications or the user-facing things on top of that. So down at the bottom, you've got your sensors and equipment, the actual boots on the ground, your HVAC systems, appliances, fire safety, lighting. On top of that, those different pieces of equipment are used in different contexts. They're used for homes, they're used in buildings, office buildings, hospitals, large commercial, small commercial. On top of this, you have management services. Today, these are usually fairly primitive. It's sort of, I want to look at my air handling unit. What, is the airflow high or is it low? But you can imagine, having a richer set of services, things that could store the history of your sensors. So you could go back and look at, maybe this room gets hot, in October every year. The ability to have schedules, the ability to have, notifications on your phone when the building's going wrong, right? There's services we can imagine. And on top of that, we can create applications for various means. This could be anything from demand response, having the way that my building operates, differ in relation to the price of energy. It could be things like occupant-driven control, the sort of the state of the art right now is you sort of program that schedule once into your little digital controller, and then you sort of cross your fingers that no one's going to take a holiday, or there's no federal holidays, or weekends don't exist. The state of the art thermostat you can buy off the shelf now for a home only has night and day settings and maybe weekday, weekend, right? So, but we can imagine even more intense, even more data-driven operations on top of this. Can I have a model of when I do this, how is my building going to respond from a thermal perspective, from an occupancy perspective? How do I adjust lighting and, in relation to the amount of sunlight that's coming in? The more information you have, the more sophisticated things that you can do, all for the purpose of energy efficiency and occupancy comfort. The problem right now is that the building world today is characterized by incredible heterogeneity. Everything is different. You have all these different building management systems. You have different versions of the building management systems. I spent a month at a university in Denmark where they have 4 different versions of the KNX building management software because they keep just adding buildings onto their campus. And they have 4 different BMS personnel, each of which is an expert in a different version. And each of these are silos, right? I buy my HVAC system from one company, my lighting system from another company, and unless I pay someone a lot of money to integrate those systems, they aren't going to speak together. This is what Marco was saying. You also have custom-designed systems and controls. The one that code is written to, do your set points or do your lighting or do your safety system. That's going to be, that code is going to be written in a specific way for that specific building, for that specific control system, as per the, whatever principles your engineer was following when they were going in to program that. And as a result, if you look at 2 buildings side by side, the systems are not going to be the same, the construction's not the same, and the way those systems are described is not even the same. So there's this incredible sort of mental barrier to trying to understand all of this at any sort of scale. And what the impact of this is that it increases the integration and commissioning costs. If I have to, so in the campus building down at Berkeley, we have a building that was built in 2015, Satarjadai Hall, Siemens building. Anytime they want to make a change, they have to call in the Siemens engineer who did the site, and they have to call in the building manager, and the 2 of them sit together in front of an Excel spreadsheet and try to point out, okay, what does AI3 mean? It's additional input 3. You have to know that that's the discharge air temperature sensor for a certain class of VAV that was installed at some later state.
Let me ask you to stand over here.
Okay.
That's okay.
Yes. So, yeah. And so when you want to look at anything, doing anything at any sort of scale, if I want to have a piece of software that does a more intelligent schedule, that has a piece of analytics that does a better job of estimating how comfortable my occupants are, or how I might better adjust my building, you have to do that all from scratch every single time, right? That doesn't happen when you open your computer. You just boot Windows, you boot Mac, or you boot Linux, right? You don't have to write your own operating system. But that's essentially what we have to do today for buildings. So what does software-defined mean in the context of the software-defined building? It essentially means that we're going to abstract away the way that buildings are different. And hopefully do that in a way that doesn't hamper our ability to do anything interesting. So there's lots of precedent for this. I've been listening to a podcast about the history of the Port of Oakland and shipping containers. Before we had shipping containers, we basically had to have a bunch of people that would carry all the stuff out of the ship and pull all the stuff inside the ship. But now everything looks the same. They all look like containers. And so you don't need to be concerned about what's inside the box. You just need to be able to move one side of the box. It drastically simplifies everything. Something like the internet, instead of having, IP and IPX and all these different proprietary protocols for having computers network together, come up with one standard that abstracts away all the ways in which computers can communicate differently, provide you one unified mechanism, and everyone just uses that. Things like peripherals, I can connect my mouse, my keyboard, my USB drive, whatever with just USB. Now with USB-C, you can even connect your monitor, you can even power your computer, all with the same sort of form factor. And same thing with operating systems, right? You don't care about the brand of your hard drive. You don't care about who wrote the control code for your Wi-Fi card or your USB stick. It just sort of works. You just sort of plug it in, and the way that you want to interact with it is the interface it provides. And what this does is abstraction provides scale. It provides a way for you to not have to spend your time, waste your time about the individual details and idiosyncrasies of all these underlying technologies and focus on what matters, which is what you want to do. And so, we want to be able to write code that's able to sort of automate the processes that right now are largely human. We want to be able to customize software, so I don't have to go and pay someone, some hourly rate to, write a schedule because everyone's taking the day off on Monday. All right, I would like to be able to do that, from my computer. I want to be able to move fast, write quick code, have, someone that's familiar with Python or JavaScript or whatever the language du jour is, and just be able to sort of make stuff happen on the building. And right now, all that's wrapped up in these proprietary boxes that are very hard to get into. And so the general question is, what if we interacted with buildings more or less the same way that we interacted with computers, where we didn't really have to know too much about what's inside, but we know enough to be able to figure out what's going wrong? And so there's this concept out there, which you may or may not have heard, is the digital twin. The fact that I have some physical building. This is the Target Hall on the campus. I've got my floor plan. I've got my devices, my dampers, my lighting controllers, my plugs. If I have sensing in there because it's a research institution, my meters. I have all that information, and it's all in there, and it's working, and it's operating. But there's a digital representation that's external to that. That's that's easier to understand. I don't have to go in and point to one device and say, oh, that's, this IP address. I can say, oh, it's a temperature sensor. Oh, it's a thermostat. It's a reheat valve. And essentially what you can do is, going from the digital twin, I can work with this using whatever tools I want. If I want to use Excel or Java or Python or some web app that someone wrote, some open source software, because if I standardize this, if I design the digital twin well and that application programming interface, then I don't have to care about what this is. It can be Siemens, it can be KNX, it can be talking over BACnet LAN, talking over serial. It could be, carrier pigeons carrying HVAC commands back and forth. As long as I have a sufficiently descriptive digital description, that doesn't matter. Which means that I can write code once and ideally run it anywhere, on any building. So the sort of vision here is there's a building app for that, right? I can take my thermal modeling app. Someone writes a really good way of predicting what's the temperature going to be in this room, provided the other actions. If it's a few people, if it's a lot of people, if we turn off the air conditioning, if we turn on the air conditioning, if we turn on the air conditioning and it breaks, what if the window's open, right? Someone writes that code. What if I could run that on any building, right? I don't have to pay someone to go and configure it specifically for my building. It just sort of works, right? Occupancy modeling. How do I, come up with a notion of when people are going to be here and when they go home without asking everybody to sign in and sign out? What information is there in the building that I can leverage to sort of infer that through data. System identification, how much energy does my equipment use? Fault detection and diagnosis, did my damper break? Model predictive control, how do I, design an optimal control algorithm to meet some bounds? Doing energy analytics, what's my energy use per square meter in this building? Personalized environmental control, demand controlled ventilation, microzones, thermal comfort. There's this huge disconnect between where academia is in terms of all these cutting edge algorithms, these new ways of devising. We can look at the difference in the damper position over the course of the day, and if you control for solar influx into the building, you can predict when people are going to be there, because you can measure how much the building is reacting to the heat generated by the human body, right? But you can't go and buy that off the shelf. There's still this disconnect between how does that software get written, these new analytics get developed, and how does it get executed on the building. And so the way that we achieve this is through interoperability. Which, there's sort of two flavors of interoperability: syntactic interoperability, which is, what does data look like when two systems talk to one another? This is, to some extent, what BACnet tries to solve. If I have a controller and a damper, how do I say, open the damper up? What it really says is, how do I communicate some number that I can send to some point in your register file so that you can open that up? It doesn't mean that it's necessarily a damper. You have to sort of know that ahead of time. But it does say, if two systems want to talk to each other, they can send data. They don't necessarily know what each other one means, but they can understand, I'm sending you, the number 3. Semantic interoperability is, how do systems commune what they mean? If I want to say, what are all the ways that this room could heat up? What is your temperature sensing here? Do you have a thermostat in this room? Is this part of a larger zone? Rooms that are all, conditioned by the same, VAV box that's in the ceiling? What's the metering infrastructure for this building, right? Is this room, what's the, the material between this room and the room next door? Do we have a lot of windows or a few windows on that side? There's all these questions we want to know. How do you communicate that information in a standard way? And so this is a little bit abstract, but essentially what you want to represent are things. That thing is a desk, it's an asset, it's an equipment, it's a sensor, and you want to represent the relationships between things. My sensor is in this room. My thermostat controls that piece of equipment. That piece of equipment has a duct. That duct connects my air handling unit to my VAV to this zone. That zone consists of these rooms. There's certain sort of principles, certain sort of fundamental descriptions about buildings that we'd like to be able to state that are true sort of no matter what kind of building you're looking at. There's always going to be rooms. Your HVAC system doesn't have to be air-based. It could be radiant. It could be water-based. But there's still connections. There's still software. How do you represent those connections of the equipment and the points and the software in a way that's not specific to a particular implementation, particular vendor? And so one thing that we've been working on is a scheme called Brick. There's a couple other things in this space which I think I forgot to put a slide in for, but the two sort of major players right here are industry foundation classes. So the question is, when I want to describe a building, what am I describing the building for? What purpose does that solve, right? I don't use blueprints to necessarily debug my HVAC system or my lighting system, right? So when you're building a building, you're constructing a building, the data format you use is a BIM. It's called IFC, Industry Foundation Classes, which describes, if I have my ducts, this is how I want you to put the ducts in the building. This is how you hook up this equipment to this piece of equipment. This is the layout of the building. This is where the damper's going to be. That's where the lights are going to be. That's what the information you need. That doesn't help you when you want to know, if there's windows on that side of the room and it's this time of day, they're going to have light over there. I want to turn the lights on the other side of the room. It's very hard to reason about that information because you don't necessarily have that at hand. Project Haystack is another open source effort that's been trying to describe the types of equipment and points that are inside buildings. I'll get into a little bit of what they're trying to do. And Brick is sort of the next step on from that. What we do is we describe the physical things, the equipment, the points, the things that are actually there. Logical things like controllers, things like schedulers that influence different pieces of equipment, and virtual entities, things like set points, which don't have a physical instantiation, but they're something that a controller is trying to make use of. And what this is going to enable is semantic interoperability, So trying to avoid vendor or site-specific labels of things. So how many of you have looked inside a building management system and you see the points that are labeled? So I've got, and that point label has to try to encode as much information about what that point does as possible. And you have to rely upon some standard that someone wrote down. If it's the Bancroft Library on the Berkeley campus, that standard is written in pencil on the back of a page that was scanned into a PDF that you can only get if someone gives you a CD-ROM and you go there in person, right? Sometimes you're lucky enough there's a binder, sometimes there's an Excel spreadsheet, and what that's gonna say is, when we've got, something dot something dot something, that first one is the name of the building, the next one is the name of the air handler unit, A1, the next one is ARS, that's air room sensor, so it's probably temperature. I've got, AI3, M304, what do these abbreviations mean? And the reason why this never really changed, for a long time nothing changed, was because you only ever had people in the same company coming to look at the building, right? You develop an intuition for what these things mean in your context, and that's sufficient for you. But if you want to have the kind of interoperability where the software I write for one building can work for another building, you need some way to generalize how those things are named. That's the problem that Haystack solves, is how do I decompose a sort of a long name into a set of tags that describe specific aspects of it. What Brick does is we say, it's not just about what you name things, it's about how those things relate to one another. It's not enough to know I've got a chiller plant and I've got an air handling unit and those have some points. I want to know, okay, well, what if my chiller plant has 2 cooling towers? What if it has, some weird design that someone came up with? The computer science building on the Berkeley campus has 3 chillers that are shared between 2 buildings, and the usage of those depends on the day of week, and probably someone flips a coin somewhere. So how do you model that, right? Haystack is only going to provide sort of a first level of description. So the way that you do this is you come up with a class structure. You have sort of fundamental things that are equipment, things that are points, things that are locations, things that are resources, and you can come up with different sort of a taxonomy of those, right? I've got different systems. I've got fire safety, I've got HVAC. What are the kinds of equipment I have in HVAC? I've got an air handling unit, a terminal unit. What are the kinds of terminal units? VAV, fan coil unit. And what you can do is you can say, instead of calling mine FCU3, I can say, whatever the label is, we can name it something that's convenient for us, but the name no longer has to convey the meaning. It just has to convey some label that's unique. And we can use a class hierarchy. We can use something like this to say, here's a definition of what this equipment is and what it does. It doesn't say how to talk to it yet, just what it is. So it facilitates the understanding. I can go in and look at this model and say, for anything that you label, I can go and look up a definition and I can understand that. And when I create a new piece of equipment, I can go and add another link into here. Or I could say, or I don't have to know necessarily what equipment you have. Say, what kinds of terminal units do you have? And it can find all the VAVs, the fan coil units, and any other kind of flavor that you come up with. So there's some abstraction there you can use. The other thing is relationships, which is how do I want to be able to model equipment is connected to equipment, points measure equipment, equipment moves some substance, if it's heated water, if it's conditioned air. I want to be able to model all of those relationships as well. And what you end up with is something like this, where you've got this digital representation where each of these sort of nodes here maps to some physical or logical or equipment or point or relation or whatnot. And you can go and basically look at one of those and say, that's a temperature sensor. It's in this room. The units are Celsius. Here's the resource of how to go read the current value of that sensor. And I can build up the relationship. Say that sensor's in room 410. Room 410 has this volume. It's on that floor. It's adjacent to these other rooms. And that information is represented, distinct from whatever the underlying technology is. And hopefully, that same description could work if this is a classroom or a hospital or an office building or a butcher shop. And so the idea is when I write my software or when I interact with my building, I don't have to care about anything below that line, right? I don't have to care necessarily what the particular equipment or the sensors is. It's all abstracted away. It's all inside the container. And I can always look inside the container if I want to know specifics. But ideally, there's a digital abstraction above that. You become agnostic to what that hardware is, what the software is underneath. And so an example of what this is, I've sort of named all the set of things. And so these are all sort of your classic names. DPR pause was, of course, a damper position, right? You know, SUP FLSP is, I think, a supply airflow set point. So we can say, let's, put actual labels on these. I don't have to decipher that anymore. Say, that's a damper position set point. That's a supply air temperature sensor. And I can connect them to say, well, that is for this damper. That damper is connected to that VAV. That V is connected to that air handler unit. And I can, go the other way and say that VAV feeds that zone. That zone consists of these rooms. And I can have labels for everything. I can have, concrete, well-defined relationships between how all these things are demonstrated. And that gives me a way to write code. What that code looks like right here is not sort of important, but I can write my stuck damper detection application. I don't have to go and look at, lines of graphs and try to figure out, is the damper stuck or not, or did, the set point just not change? And it did a really good job. I can go and write code that automates that process for me, and that code can operate against, ideally, any building. If it's, if it's KNX building, if it's a Schneider Electric building, if it's a BACnet building, and I can go and write that application. It can run anywhere, right? The same way I can run Word on any computer. I can run my, email on any sort of computer. I could run an analytics application on any building. The other part of this is the syntactic abstraction, which is how do I try and generalize how I talk to the equipment in the building. And here you want to standardize the read and write interfaces. So right now you send a packet, you send a BACnet analog input, analog binary output to some register that's written down somewhere, and that tells you when you write this value to there, it means this specific thing. In our computer science building, which I've done a lot of work on, we have one point that means it's the reheat amount in the HVAC system if it's greater than 50, and it's the damper position if it's less than 50. How we found that out, I have no idea. I think someone talked to the engineer that did it, but that's, like, how do you, when you're writing controls against buildings, when you're trying to interact with something, how do you generalize that? Especially with off-the-shelf devices. If I buy a Nest thermostat, or I buy a Honeywell thermostat, and I buy, a smart plug that lets me know how much, my equipment is using, and I buy some temperature sensors from some startup, how does that all talk to one another? How do I generalize how I speak to that? And one way of doing that is through a reusable software component called a driver, which gives you sort of a common programming interface. If I have a VAV, I can set the airflow, I can read the airflow, I can change the reheat set point. I don't have to worry about if it's BACnet or whatever protocol underneath the covers. I just sort of write the code, and it figures the rest out for me. So we've been putting this into a large system. This is sort of the 30,000-foot view of the kinds of systems that we're building today, where I've got sort of an on-premises machine that talks to my building management system, sort of like the Niagara box that Mark was talking about. It talks to my building management system. It talks to sensor networks that I can buy off the shelf. It talks to IoT devices. Talks to my smart meter over Zigbee, and it exposes a standard interface. So I don't have to care about the brands or the interfaces or anything of the rest of that. It gives me a standard interface, and on top of that, I can go and I can save that data in the cloud. I can go and run my big data machine learning analytics on top of that. I can go and create models that allow me to reason about how my building's going to change when the weather changes or when stuff breaks. I can go and have it respond, integrate with the grid a lot easier. I can do demand response. And that's actually what we've been doing with this so far. We have 20 buildings across California. A few of them are building management systems. A lot more of them are just sort of RTUs and thermostats and smart meters. And we're able to write sort of a few lines of code. I mean, it's about 100. But that one piece of code runs on all 20 buildings without needing to change too much. And it does demand response. We can change the price of energy either through receiving an actual event through PG&E or through generating our own sort of test event, and the building reacts accordingly. And we can go and look at logs, we can go and look at the saved data, and we can go and figure out how well it went, what went wrong, and then we can go and automate that own process and sort of do this at a very, very large scale without needing to worry about all the nuts and bolts of that one is just it's a 30-year-old HVAC system that runs a BMS, and this one is just thermostats, and this one is just a guy in a room with a space heater. And be able to integrate with electric vehicles, all sorts of new resources. The other things that we're doing is working on reproducibility. If someone comes up with an algorithm for testing, how well a piece of equipment works, how efficient it is, why isn't that code more generally available? So we've been assembling a data set. Right now it's 107 buildings, 13.5 billion data points, 26,000 data streams from all over California. We're expanding that a little bit soon, but basically it becomes possible to write analytics in a way that can be verified and more robustly and at scale. It doesn't have to be anything that's a particular one proprietary implementation for your building. It might be that someday you can go and download some open source analytics off the internet and run it on your building without having to write a single line of code yourself. So that's sort of that's the vision. There's some links if you want to read more. And feel free, please to email me, reach out if you have any questions. And that's what I have. Thanks.